In this video we're going to use polar coordinates to work out the area of this region here. So in polar coordinates we've seen that a vertical line at A is given by this, and the bell-shaped curve here is given by this. So let's try and understand why a vertical line in polar coordinates is given by this. So if you're working polar coordinates, you're moving along like this. So you're scanning your angle in this manner, and then you've got a vertical line here. So for any given angle, let's say theta being this or theta being this, at any given angle the radius is given by this because let's say this angle here is theta, and you're looking at this triangle here. This length here is A. So you've got a triangle like this. A, the angle here is theta. What is the radius? What is the radius? What is the radius as the angle increases? So whatever the angle is, so cos theta equals A over R, and the radius is given by this, which is A secant theta. So no matter what the angle is, you can always work out the radius. You can always work out the radius, and the radius is given by this. So well, we've seen this before. So a vertical line in polar form will be given by this. Let me explain the bell-shaped curve. So the bell-shaped curve, which is this curve here, let's visualize this as 1 over cos. So this is our cos graph, but so it's moving along like this. The angle is scanning along like this. So let's say when it gets to very close to 90 degrees, pi over 2, which is somewhere around here, just before it gets to pi over 2, because dead on pi over 2 it breaks down. This thing here breaks down. This thing here breaks down. But just before pi over 2, cos theta would be very, very, very small. So this number here would be very, very small. 1 divided by a very, very small number, it would be a very, very big number. That's why your radius, this is going to become insignificant in relation to this as theta gets very, very small. But the point here is that just before it gets to 90 degrees, so you're moving along like this, just before it gets to 90 degrees, you can see that this quantity here would be very, very big, and then you times by our constant A here, it's going to be, the whole thing here would be very, very big. That's why just before it gets to 90 degrees your radius is very, 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 very big. That's why it's really far away. And then just after 90 degrees, this quantity here would be a negative number, but very, very small. So you can imagine this quantity here to be negative 0.0000000, let's say 3. So this thing here would be very, very, very big, but negative big. So this whole quantity here would be very, very big, but negative big, if that makes sense. So imagine this quantity here as being negative 9999, a really big negative number, and then you times this here, so that will give you a negative radius that is very, very big. So what that means is just after 90 degrees here, just after 90 degrees, let's just imagine it to be this angle here, just after 90 degrees. So imagine this, it will give you a radius that's very, very negative big. So what that means is when the angle is pointing in this direction, your radius would be negative, meaning it's in the opposite direction and it's very, very big. So let me just elaborate on this. Hang on. So the angle is moving along like this. It's scanning in polar form, is scanning like this. When it gets to near 90 degrees, the radius will be really, really big. So it points all the way up there, which kind of makes sense because the radius is very, very big. Now dead on 90 degrees, pi over 2, it will break down, but just after the 90 degrees it will give you a very big negative radius. So negative radius would be you moving in the opposite direction, and it's very, very big, so it points down here. and then as it moves over here, it's going to point somewhere negative radius here, and then as your radius is pointing over here, it's going to point here, and then as you move over, as you're pointing this direction, it's going to move to this radius, and then as you're approaching here, if you're pointing this direction, the radius will be this much, and so on. So what it's doing is that as you're scanning like this, what it's doing is it's doing this. As you're scanning like this, it's doing this. Hang on, it's pointing to here, it's pointing to here, it's pointing to here, it's pointing to here, and it gets very, very big as you approach 90 degrees. Just after 90 degrees, all of a sudden, it points in the negative radius down here, and then it points here, and then it points here. So that's what's going on. So if you want to work out this area, you need to do this. Hang on. If you want to work out this area here, you would need to do this, because hang on. So you're scanning along like this. You're scanning along like this. You're scanning along like this. So you're integrating from this line, and then you stop at this line, which is this thing here, and then you're scanning all the way. Remember, you're scanning like this, so up to 0 to 90, but that will only give you half of the bell shape. That's why you need to times 2. Yeah, so the area is given by this. I hope you can follow that. Technically, you're not allowed to plug in pi over 2, because this thing here breaks down pi over 2. But technically, if you were to do this, you would integrate it from an angle of 0 to an angle, I don't know, let's say beta, and then take the limit as beta tends to pi over 2. Technically, you should do this, but let's take a shortcut and be lazy. Let's just do it from 0 to pi over 2. It will have the same effect. So technically, by right, you should do this, but let's take a shortcut. Let's just do it from 0 to pi over 2. Well, anyway, the area is given by this. So now it's just a matter of evaluating this. So this r here, integrated with respect to r, that would be r squared over 2 from here to here, from here to here. So now this thing here is a constant. So take the constants out. So that will then give us this, and then put this whole thing here into here. That will then give you this. Take away, put this thing into here. That will then give you this, and then factor out the a squared, so you can actually take it out. That will then take you to here, and then imagine this as being 1 over cos. Yeah, and then imagine this thing here. Well, basically, we want to merge these two together. Merging these two together will then give us this thing here, and then imagine this thing here as 1 over cos squared. So we can merge, well, same denominator. You can merge it into one fraction. Multiply this out. That will then give you this. You've got your take away 1, and then it simplifies to this, because these two would cancel out. These two would cancel out, giving you a 2, and then to the power 4 over squared would then give you this. So it's really a matter of us integrating this thing here. Remember, a long time ago, to integrate this, we would imagine it to be like this. So this thing here, imagine this as this. So merge these two together. That will then give you 5 over 2. But then when you integrate it, it gives you 5 over 2 theta. And then integrating this will then give you this from theta equals 0 to theta equals pi over 2, 0 pi over 2, and then put this into here. That will then give you this. Put this into here, which would be 0. So and then you take away. Put this into here, which would be 0. Put this into here, which would be 0. So the area is given by this. Tidy this up. So the overall area is this. Okay.